In my opinion, there's three approaches to doing research in this field. The first is numerics, the second is an experimental, and the third is theoretical. I think that most people spend their time in engineering and physics in the numerical world. And by that I mean solving the equations or finding approximations of them with digital computers. This is called computational fluid dynamics. This part of the field I've written and produced lecture notes and a series of videos, which is also posted online. You can also find those notes online. And I think this just means that, in a sense, that we're too ignorant to be able to solve the equations analytically. Nobody's really found general analytical solutions, that is, closed-form solutions without assumptions of any turbulent flow. And because turbulent flow is prevalent and so important to engineering, we try and integrate and find solutions of the equations with computational fluid dynamics, which means just using a digital computer to find approximations or discrete solutions of the equations of motion or variations of them. I think you'll find that most people in industry work in numerics at the end of the day, and most of the effort in the research communities and universities seems to be in numerical methods or variations of them kind, and that encompasses everything. For example, if there's a machine learning or AI or reduced order modeling or spectral analysis, fast solutions, study solvers, linear algebra solvers, all these types of things all fall into numerics. And I feel also that so many people spend so much of their time in the computational world and they focus more on the numerical methodologies of the computers than they do the actual equations and the physics. In some sense, this is the greatest strategy because we focus so much of our effort here and not thinking about the equations and their physics. And this is just unfortunate, I think. Maybe a smaller group of people work in experimental work, and I would classify that as, using nature, not like mathematics and necessarily. I mean, there's a lot of math in experimental work. But actually doing flight tests or wind tunnel tests or ocean measurements or atmospheric measurements, measurements of blood, anything where we actually take a measurement or do an experiment with a fluid, natural fluid dynamics, man-made fluid dynamics. I don't think a lot of people work in this area today, mainly because of the expense. And if we can do something numerically, correctly, cheaper and faster, then that's probably a way to go. The counterexample to this is that there's so many experiments or even flight tests that you just cannot repeat numerically. And I think that in my career I've seen a lot of perhaps government leaders saying we can get rid of our country's wind tunnels. I don't think we're ever going to get rid of our country's wind tunnels because the computational fluid dynamics just doesn't match flight test and experiment in so many situations. Or if we are able to get rid of our experimental facilities, we'll have understood the physics and mathematics so well that we can just do it with computers. I'm not so confident this will happen in my lifetime, but maybe it will happen in yours. Finally, there's theoretical and analytical approaches, and by this I mean the classical approaches that the ancients used in their modeling. By ancients, I mean those described by Jean-Roland and D'Alembert, and that we work with mathematics and analysis and perhaps our own minds to understand the physics and equations. And that's what this class is really all about and what I love doing. So this is the path we'll go forward in these particular lectures, I think. And there's plenty of material on CFD everywhere, all the time, and less material on experiments. There's very, very little material in this category. I also think this category is the most difficult because there's been so many amazing and intelligent people who have worked on it over the courses of their lives and made so little progress or just quit. I think that Heisenberg wrote his Ph.D. dissertation on turbulence, and he left and invented quantum mechanics. And as I mentioned earlier in these video series, there are different people joking that when they pass away and go to heaven, they'll ask God about the physics of turbulence to understand it, or even why does it exist. I think this last approach also feels hopeless. And if you want to have a career where you actually make progress and have something tangible, it might be good to go on the first two if you love fluid dynamics. So I think a feeling of hopelessness and overwhelming complexity often comes from studying the equations.